Okay, so this is the Tuesday, November 28th class, and this is the short class I'll have because I have something I need to go to here in a little bit, and we have two more classes after this. But Thursday I was planning to go from 6 to 7:30 to make up some of the time from tonight's class, and okay, so I wanted to talk a little bit about test 2. I know people, I don't think, did as well on the second test as the first test. And after grading your tests, I know there were a lot of mistakes, but they were made based either on how students didn't understand some of the concepts of chapter 4 that we talked about repeatedly, or there were mistakes because students did not read a test 2 problem carefully. Like on a lot of tests, there are different mistakes made by people, different types of mistakes are made. And there were also mistakes made that were actually basic algebra errors that students begin making in freshman algebra class. So I sent back your graded test today, so you can read what I have in the notes on the graded test. I do get the feeling from grading your test that students haven't been paying attention to what's discussed in class. And I feel, I'll talk more about this, because teaching a class completely remotely to remote students, I've taught classes where I had face-to-face students who were in person, and then maybe have one or maybe two that were remote. But I haven't had a class where all the students were remote. So I'll talk a little bit more about how I want to finish the semester. So these test problems from test 2 were based on your homework from chapters 3 and 4, and I know you know that, and the concepts that have been discussed and proved during class. I think it's a good idea to correct your test 2, since I will put some of these same ideas and problems on test 3, which will be given during finals week, since I think the connection between the analyticity of functions that came up in chapter 3 and properties of integrals from chapter 4 are important to this course. So I'll discuss some of these problems in more detail soon. If not the next class, then the one after, because we really just have 2 class periods, even though the times might be a little bit longer to make up the time of this shortened class. Beyond the new homework from chapters 5 and 7, that is new for test 3, because the 9 problems from chapter 5 are what's due this week, this Thursday or Friday, and I'll assign just a few from chapter 7. I'm working on examples to show you, because some of the integration techniques now are really kind of interesting. And I'll give you some practice problems for topics from test 2 and chapters 3 and 4 to help you correct some of these concepts and problems from this second unit. So in addition to the problems from chapters 5 and 7, I want to revisit some of the concepts from chapters 3 and 4. And I'll give you some practice problems that will help you with that. And then the others will be just from the homework from chapters 5 and 7. Like I say, there's 9 problems from chapters 5, and I'll only assign about 3 or 4 from chapter 7. Now those are kind of interesting, but I'll show you, we'll see how much time I have to talk about examples tonight. And if I don't have time, we'll finish more of that tomorrow on Thursday. Okay, so remember also that in an upper division undergraduate math course, students are expected to explain their answers and to even argue or prove why their answers are correct. So one thing I want to do is I'll take test 2 corrections that you make and submit to me. I'll use that to replace your lowest homework assignment from the first 2 units, units 1 and 2, but not the ones that are new that you're working on currently. I'll also give you practice problems for test 3 Thursday or Friday. I mean, if I don't have them ready for class on Thursday, I'll get them to you on Friday before the weekend. And I may give you individualized homework for chapter 7 that will count on test 3. So we'll see how that goes. So anyway, I wanted to say those things about test 2. And I guess, those are recorded now on that. So, okay, so let's look at some more examples then from, remember, let's just review what we had. We were using the residue theorem, and we were asked here to prove that this real integral, and this is the fascinating thing to me, is that we can use complex variables to evaluate real integrals. So this, usually when you see x, it means a real variable like y. And z would represent x plus iy, the complex variable. And so we can use complex variables to prove that this integral equals 7 pi over 50. And when I've tried to enter this like into either a TI-89, I mentioned this in the last class, or like Scientific Workplace has a sort of an underlying computer algebra system, MooPad, and I've tried it with that, and it can only give me an approximation. It can't give me this nice exact form. So I still feel like human beings can do math, can do some math that computers and calculators aren't able to do yet. So just to kind of remind ourselves what we did. So we defined C in the complex plane. So z equals x plus iy, where y is 0 and x is between minus r to r. And along with a sort of a half circle in the complex plane, z equals r e to the I theta. And so theta ranges from 0 to pi radians. So just to remind you what the picture looks like, that's what this picture looks like here, where r is greater than 0 is chosen sufficiently large to contain the poles of f, where f is defined to be, it's like we're extending this real integram, this real valued function into the complex plane. And so we're also assuming image of z is greater or equal to 0, y is greater or equal to 0. So find the poles of f. So we set each of the factors of the denominator equal to 0, and we solved and got z's plus or minus I, and this we solved the quadratic. I don't want to talk through like we did in the last class, but just to kind of remind you, we had 2 solutions for this. And so based on how we define C, there are really just 2 poles of F that are inside of C. So the poles of F contained inside C are Z equals I, and that's of order 2 because of how we have this the polynomial for which I is a solution is raised to the second power, and then this quadratic has 2 solutions. These 2 solutions, and only one of them, minus 1 plus I, is within C. You can see that here. And that's a simple pole, a pole of order 1. And so by the residue theorem, this integral will be equal to 2 pi I times the sum of the residues, where A is, so A sub minus 1 represents the residue that corresponds to I, the pole I, and B sub minus 1 is a residue that corresponds to B equals minus 1 plus I. Remember, we got that from having a Laurent expansion where we had positive and negative powers of the variable, and so we had the subscripts were integers. We had positive subscripts positive integer subscripts and negative integer subscripts. And it's like the only thing that didn't go to 0 were these two here. And that's what allowed us to find the integral. So the residue of z equals I, we actually define a function to be the derivative of, okay, so when the pole is of order 2, like I is, then what we do is to find the residues, we multiply the f of z by z minus I squared. And we, if it's an order 2, then we'll take the derivative one time. And this is sort of what we had to do in order to isolate this a sub minus 1 in the Laurent expansion. That's where that came from. And so that gets a little messy. You know, we had to follow kind of the quotient rule, but we canceled this one out. We worked that out. And, you know, you can simplify because we only needed to take the derivative once, so you don't really need to simplify a lot. If you have to take the derivative twice, then you need to kind of do more simplifying before you take the next derivative. That's if you have something of order 3, when you need to do that. So we went ahead, and so what we do is multiply by z minus the pole raised to whatever power we have for its order, and then take the derivative a number of times, one less than the order, and that defined h, and then we take the limit as z approaches I. Let's see, that's not written too well here. Yeah, z approaches I, which means for this, we can basically just substitute I in for z and kind of simplify it down. And so then we worked it down to just this complex number. Okay, and then we found the residue for z equals minus 1 plus I. Since it's a simple pole, we don't have to take any derivatives. We just multiply by z minus negative 1 plus I, which really, as you can see, is the same as z plus 1 minus I. And that cancels, and we take the limit and plug, you know, I guess that z probably should have been minus 1 plus I, but it becomes that over here. And then you work it out and work it down to a complex number, 3 minus 4i over 25. So by the residue theorem, this integral here is 2 pi I times the sum of the residues, which we found to be these complex numbers. And that gave us actually an pure imaginary number, but since we're multiplying by 2 pi I, we actually ended up with a real number. And so that tells us, that implies that this real number is equal to this complex integral, but that equals to this, the sum of these integrals, where this is a real integral from minus r to r, and we'll take the limit as r goes to infinity. And the same with this. This is the half circle. Gamma sub r is the half circle on the complex plane. So if it can be shown that this part, as we let r go to infinity, equals 0, then that would show that that this integral where we have infinity, you know, we take the limit, you know, that's how you, this, in some ways, this is like a, what's the word I'm looking for? When you have the, infinity is one of the limits of integration. An improper integral, I forget the terminology now, but you have to kind of evaluate it in terms of a parameter and then take the limit after you work it out. And that's what we'll do to actually find the integral that we're looking for, which is this one here. And so if we can show that this part goes to 0, then when we take the limit, we'll get all that will equal 7 pi over 50. So in order to prove that's true, there's a certain amount of work to be done. All right, so I didn't want to take time in this class, this shortened class, to show why this would go to 0. So in the meantime, for the rest of this class, for the next 20 minutes remaining of this class, because I need to end class at 6:45. I may have started at 5 minutes later, though, so this may end up being a 40-minute class, but we can make that up at another time. Okay, so here's another one where it's a little bit different. So I want to do another example. So I'll do a few more examples, and that might be all the new material we need. Like I say, I want to try to emphasize and go back over some of the topics and concepts from the second test. All right, so let's evaluate this integral. So this will go from 0 to 2 pi cosine of 3 theta d theta over 5 minus 3 times cosine theta. Okay, so let's let z be equal to e to the I theta and once again theta ranges from 0 to 2 pi. Now we're going to make a substitution here and rewrite this integral in terms of z, and we'll see what we come up with, and we'll use we'll make substitutions to rewrite this as a function of z, and then we'll see what we have to work with there. All right, so if z is equal to this, then dz d theta. I like a lot of the detail people put in their work, whether it's the homework or the test, and so the derivative of z with respect to theta, as you know, would be e to the I theta times the derivative of the exponent with respect to theta, which gives you just I. And so the dz, the differential in z, is equal to I times e to the I theta d theta. Okay, so now we know that e to the I theta equals cosine of theta plus I sine of theta. And rather than try to memorize some things that we've used, let's just use this fact here. If we have, this is just, this is Euler's identity, right? One of the great mathematicians of all time, lived in the 1700s. And he really completed, and also he really kind of taught people how to use complex numbers and arithmetic and so on. So if we let theta be minus theta, we get e to the minus I theta, and we get cosine of minus theta plus I times sine of minus theta. But remember, this is just real functions that you had in trig class, and cosine is an even function, so that's equal to cosine of minus theta is cosine of theta. Sine is an odd function, so we can, it kind of looks like we're pulling the minus sign out, right? So we can do that. And then, so if we add these two together, that will give us e to the I theta plus e to the minus I theta. I'm going to add these together. It's like, you know, you can add equations together this way because it's like you're adding equal things to both sides. So we get 2 cosine theta. And I know you know a lot of this stuff. I can tell from your work. You guys have a lot of experience in math, and but you know, in some ways, it's my job to help you nurture those math abilities. But also, I need to kind of show you and kind of challenge you too, right? And so, if you get challenged in math, you'll know it because, you know, I guess we've all been there where we make a mistake and so forth. Yeah, and then when we add these, the signs cancel out, right? So we get 2 cosine theta. So we can use this to solve for cosine and get e to the I theta plus e to the minus I theta divided by 2, right? Okay. Okay, so we need for this, we need not only cosine theta, but we need cosine of 3 theta. Now, one thing you may notice is that e to the I theta is z, right? So I can put in here z, but maybe I'll write it right over here. What if you had z to the minus 1 based on this definition? Because we defined z to be this, right? If you had z to the minus 1, that would be the same as e to the I theta to the minus 1. And that's the same, you know, by properties of exponents, you know, you multiply the exponents and get e to the minus I theta. And so e to the I theta is z, and e to the minus I theta is z to the minus 1. So we'll have that over 2. Now, here we have, for cosine 3 theta, we can put 3 theta in for theta. We'll have I times 3 theta plus e to the minus I 3 theta. And, okay. And, oh yeah, we forgot the over 2 part. But really, this is the same as e to the I theta cubed, right? Yeah, e to the I 3 theta is the same as that. And e to the minus 3I theta is the same as e to the minus I theta to the third, because that's where you multiply the exponents. But, as we said, e to the I theta is z, and e to the minus I theta is z to the minus 1. So we can rewrite this as z to the third plus z to the minus 1 to the third over 2. And that's really the same as z to the third plus z to the minus third over 2, right? So we can almost substitute everything we have for theta and for z. We have cosine 3 theta. And it's really just based on this definition, right? We have, yeah. So we need to do some of this too. All right. Yeah, let's backtrack what we have here. We have z equals this, so we have, and so that means that z to the minus 1 is this, and take the derivative of z with respect to theta, and we have that, and so we have dz is equal to this, and then based on this, the Euler's identity and the fact that cosine is even and sine is odd, we get 2 times cosine theta equals this, and cosine theta is equal to this, which is the same as z plus z to the minus 1, based on what we figured out up here, over 2. And cosine of 3 theta is, we can just plug 3 theta in for theta here, but that's the same as this. And then that's the same as, because z is e to the I theta, that's z to the third, and this is equal to z to the minus 1, so we get that. All right, so so the only thing left with theta in it is the d theta, right? So we know that dz is equal to I e to the I theta d theta. So yeah, let's solve for d theta. So d theta will equal dz over I e to the I theta, but remember, e to the I theta is z, so this gives you dz over iz, and that's what we'll plug in for d theta, right? Okay. Let me just check on something here. All right. Yeah. So in some ways, z is just a circle, but it gives you like a C, a curve C, and that's how that's the notation we'll use when we switch over. So we switch that over now. We'll just put a like a C here, and yeah, so C is really a circle, and we know how it's defined and how it's parameterized. That was just how we defined it to begin with. But I'm just kind of restating it now because I'm going to use this notation for C now that I hadn't used C in this problem yet. And but that's really the same as this, how we represent circles in the complex plane. Okay, so cosine 3 theta now is this here. z to the third plus z to the minus third over 2. And then we have 5 minus, and then the cosine theta, so we can write it in this way. So cosine theta is this, and cosine 3 theta is this in terms of z. And okay, so yeah, we left out the d theta. So the d theta now is dz over iz. That's our d theta. So let's see how we can simplify all this. Do some algebra here. All right. And then we'll use actually, we'll use residues to figure this integral. But we won't have to do that thing where we let r go to infinity, because we're really just integrating around this circle. Okay, so let's rewrite this so we can kind of simplify things, because what we have here is z to the, I'm going to write it out this way, z to the third plus 1 over z to the third. Then we have a factor of 1/2 in there, based on what we have here, and then here we have, let me see if I can write this differently. Maybe I can write it this way. 10 minus 3z minus 3 over z, and then all of this is multiplied by 1/2, and that would still give us what we have here. If you distribute the 1/2, you'd have the 5, and then you'd have all of this divided by 2. So that would be fine if we wrote it that way. Okay, so then so the 1/2 will actually cancel. So here's what we can do. We have like a compound fraction. We have little fractions inside of a big fraction. So I think if you multiply the numerator and denominator of the big fraction by the least common denominator of the little fractions or minor fractions, that will turn your compound fraction into a simple fraction, where you only have one fraction bar. So let's try that. All right. We'll multiply by, z to the third is the sort of like the least common denominator of the little fractions, because we have 1 over z here and then 1 over z cubed. So we'll multiply this stuff over here by z to the third, and we still have the dz here. All right, so if we distribute the z to the third, what do we have here? Z to the 6 plus 1 dz, and then here we'll have 10 z to the third minus 3 z to the fourth minus 3z squared. Okay, and oh yeah, we also dropped the factor of I here also, right? So we have, if we multiply by minus I to the numerator and denominator, yeah, let's make sure I'm going to bring that out here, like 1 over I, we'll do that. And that way I haven't, I need to put that in there. Okay, 1 over I, we can factor that out through the integral since it's a constant. Let's see what we have here. Okay, all right. I think we're on track here. All right, so I'm going to go ahead and multiply by minus I to the numerator and denominator just to kind of take care of that constant on the outside there. That way we won't have 1 over I. We'll be multiplied by minus I over minus I. We'll end up with minus I over 1, right? Okay. And now, oops. Now, yeah, so then here's a common factor of z squared we can take out. So I'll factor out a z squared. And let's see, if I write this in descending order of powers, then I'll have a minus 3z squared plus 10z minus 3 here, right? Okay. And so the minus z minus I, but I could also bring out a minus sign, and that'll give me a positive leading coefficient. We might see if we can factor this, but before I do that, so I don't get too confused with the signs, we'll factor out a minus 1 from this trinomial here and bring that out, and this is equal to minus I, right? So if I bring out a minus, then that'll become a positive I, but okay, so we'll just do like this. We'll have a minus z squared, 3z squared minus 10z plus 3. And okay. Now the minuses will cancel here, right? Let's just make sure we still have what we had on the previous line here. All right, yeah. Just factoring out a minus 1 there. Okay, so that'll leave me with a positive I on the outside there. And then I'll have z to the 6 plus 1 dz. And then down here, I'll just have z squared. So we can see now we'll have z equals 0 will be a pole of order 2. Now let's see if we can factor this one. If we can factor it, then we'll have a 3z here and a z there. And let's see. So if we have minus 1 and minus z3 here, let's see, that'll give me minus 9z plus minus z. So that'll be minus 10z. And then we'll also have a positive 3. So I think it does factor this way. And now we can see what our other poles are. Okay. So, yeah. So remember, we're integrating around a circle of radius 1. And within that circle of radius 1, 0 will be inside that. And this will give us a pole of 1/3, a simple pole of 1/3. And this will be 0 will be a pole of order 2. But now the other one, 3, is outside the circle, unit circle. So we won't have to worry about that one. And it's analytic. This function is analytic. I was reading the residue theorem earlier, and since we're about to run out of time tonight, it'll be 6:45. This would be a good place to pick this up on Thursday. We can kind of review the changes on Thursday, but before we do, let's read the residue theorem. It's in chapter 7. Let's read what it says here. That way, make sure everything looks right here. Let f of z be a single valued and analytic inside and on a simple closed curve C, except of the singularities A, B, C inside of C, which have residues given by A sub minus 1, B sub minus 1, C sub minus 1. Then the residue theorem says that the integral will equal 2 pi I times the sum of the residues. In other words, the integral of f of z around C is 2 pi I times the sum of the residues of f of z at the singularities enclosed by C. Note that 7.7 is a generalization of 7.3. Cauchy's theorem and integral formulas are special cases of this theorem. Yeah. So 7.7, they must be signifying. Oh, this is I guess 7.3. 7.7, let's just remind ourselves what that was. Okay. Oh, no, they're talking about the equation 7.7. Okay. It's a generalization of 7.3, and 7.3 was, okay, yeah. All right. And, okay. All right, so that's where we'll pick that up. We'll be looking at the residues of this integral in order to apply the residue theorem to evaluate this integral, and we'll pick that up next time, and that'll help us to evaluate this using exact form. Okay, so it's about 6:45, so we'll end the class there tonight, but keep track of anything, and if you miss class, be sure to look at the lecture recordings and put in that time. And we'll talk more about some things we'll do to end the semester. And okay. All right, so yeah, all right. Well, have a good night.